All right, so what we're going to do now is we're going to look at some things about optimization. So as a reminder, we are looking at sort of 3 books here. So one of them is Convex Optimization. And this is by Boyd and Vandenberg. Then we also have the book Numerical Optimization. And this one's going to be by Nocedal and Wright. And then the other one is going to be the calculus book by Stewart. And so where we left off in class was that we had gone through some of the definitions of convex functions and convex sets so that we had some clarity on what those were. And then we had started looking at the fundamentals of unconstrained optimization. And so the idea for this is that an unconstrained optimization problem would be minimized by selecting decision variables which cause f of x to be as small as possible, where x can be in Rn. And so we are going to make a requirement that this f of x is going to need to be sufficiently smooth to help us with some of what we are doing. And so where we had left off in class was that we had written out Taylor's theorem. So I'm going to write what Taylor's theorem is from the numerical optimization book. So Taylor's theorem is as follows. And so this is from the numerical optimization book. I'm just going to copy what it says. So suppose that your objective function f maps from Rn to R is continuously differentiable and P is in Rn. So this means P is a vector with n components. Then f of x plus P equals f of x plus del f of x plus TP transpose P for some t in 0 to 1. Moreover, if f is twice continuously differentiable, then del f of x plus P equals del f of x plus the integral from 0 to 1 of del squared f of x plus TP P dt, and f of x plus P equals f of x plus del f of x transpose P plus 1/2 P transpose del squared f of x plus TP P for some t in 0 to 1. And so we left off right here last time. And what we said was, okay, well, that's great, I guess. But even though in our class so far, we've done a lot with our linear algebra, so we're clear now on things like what this transpose notation means, what it means for like P to B and Rn, all these different things, but we haven't yet reviewed some of the multivariable calculus that is relevant to this. And so in order to really understand what a lot of this notation is saying, and to understand actually a lot of the theory that goes on in optimization, we actually have to review some of our multivariable calculus going back to Stewart. And so I'm going to start today with a few, with a bit of a discussion going back to some of that stuff from Stewart really quick. And I do want to start by making some distinguishments between this vector or this function that takes a vector and maps it into a scalar versus the vector functions that will take a scalar and map it into a vector, and just make sure everyone's clear on the notation and things in case you haven't done this in a long time. So here is what we're going to start with. We're going to start with something that is not the same as what we are looking at here, but is actually important in other ways. It's not, I guess when I say it's not what we're looking at here, it's not the objective function form. It is an important form for still some of this other notation, but it's just not the form of the objective function. So in our objective function, just to make this note, so the objective function here is going to map from Rn to R. But the thing that I'm going to talk about first is not this. I'm going to talk about something that is a vector function. So a vector valued function or a vector function. And you can find some of these things in your textbook in chapters 15 to 16. So this will be like chapters, this is things that are in chapter 15. So as a reminder of 3D calculus stuff, and based on everything that we've done so far with vector spaces and things like that, you can imagine these things extending quite readily to more than 3 dimensions. But we could say that a vector function of one variable is a vector f of t equals x of t I plus y of t j plus z of t k. And so the reason it is a function of one variable here is that you can see that this t is a scalar. So each of the arguments of f, so f of t could be written as x of t, y of t, z of t, and each argument of all of these functions is only the scalar t. Now it happens that f itself is a vector, so this is a case where f is going to map from a real number to a vector, in this case to R3 specifically. And so you can see that that's different than what we've got up here. It's like the opposite. And so we can define all kinds of things for functions of this type, things like what it means for them to be continuous, what it means for them to be differentiable. And so for completeness here, let me write a few different points, because these are important to see the difference and just to remind yourself. So for a vector function, we would define something like the limit as t goes to a of r of t if r of t is equal to this f of t, g of t, h of t, where again, the brackets here, these don't mean the inner product in this notation. This is just going back to that sort of weird multivariable calculus notation that to me looks really strange because it looks like an inner product, but just using this one because this was what was in the Stewart book that I was looking at. This is the limit as t goes to a of f of t, the limit as t goes to a of g of t, and the limit as t goes to a of h of t if each of the limits there exists. And then also we can talk about something like continuity. So going back to this f, we could say that this f of t is continuous T0 if each component would be your x of t, y of t, and z of t is continuous at T0. And then we would also be able to say like f of t is differentiable at T0 if each component is differentiable at T0. And because limits are defined like this for these vector functions, you can get the derivative of this f of t as being equal to x prime of t, y prime of t, and z prime of t. And you could think of that by going back to your definitions of derivatives related to limits. And you would say, oh yeah, well, if I'm taking the limit into each of these, then I could see how I would need to do the derivative of each component in order to get the derivative of the vector. And so sometimes people talk about these vector functions as being related to curves. So let me write one more thing in this other corner. So what the Stewart book says is it says that if f of t is equal to x of t I plus y of t j plus z of t k is the position vector of a curve C given parametrically by x equals x of t, y equals y of t, and z equals z of t. And so that might sound a little confusing, but let's take f of t is equal to cosine of 4t, t, and sine of 4t. So let's say that this was the vector function and that you only looked at t in this range between -3/2 and 3/2. So then if you draw your 3D space over here, then you would be able to get some type of curve that has some like squiggle or something in it. But so the idea with this being a curve is that at time like t is 0, for example, you would see that this would be for t is 0, this would be cosine of 0, which is 1, this would be 0, and this would be sine of 0, which is 0. So you would be at the point 1, 1, 1, 0, 0. And then when t is like 0.5, you would plug those all in and it would give you another point. And so if you trace out where it's going with time in the 3D space, you'd be able to get some type of curve thing. And so that is that point. And then there's also some stuff that's in that book about like, okay, you can get things like arc length and curvature. And so that's fine. That can also be done as well, related to getting like the length of some segment of your curve and stuff like this. So, okay, so those were the main points I wanted to make about this type of thing, these vector valued functions. And now what I want people to keep in mind is that this is distinct from a, this is distinct from the type of thing that you have for your objective functions. Oh, sorry, I'm just pulling up the right page of notes again over here. Okay, so now we're going to go to a case where we have a type of function that's different than this. So this one is a function, it has a single argument, but it just has, it like returns a vector. So now we're going to instead, remember this is distinct from that, look at a case where we have a function f mapping from Rn to R. So this is more like what your objective function is doing. It's taking a vector of your decision variables and mapping it to a scalar, because generally the objective functions of optimization problems are scalars. And so we might have something like this. So like say that you have z equals some function of x and y. So these x and y here are your independent variables, and then this would be your dependent variable. And so you can define a lot of interesting stuff. So just like how before we spent a lot of time talking about things like what are limits, what are derivatives, etc. Let's start extending this to multiple dimensions. So in this case, we're going to look at the case that we just have x and y as the arguments, but you could imagine this extending quite readily to a case where you have like n different variables as the arguments. So when we write the limit of xy goes to ab of f of xy is equal to L, what this means is that the values of f of xy approach L as xy approaches AB along any path that stays in the domain of F. And so you could also do some epsilon delta type definitions for these types of things. So I'm going to present one that is for the more general case then. So this I think you can see the idea with only this 2D case, that what would happen is if you have this function of f of xy that you could imagine that as you change x and y and you make them get closer and closer to a, b, no matter how you do it, no matter if you're getting x to go closer to a from below while y is getting closer to b from above, and et cetera, no matter how you get there, this limit holds for every case. So if you have some weird function where that's not true, then you would not have a limit like this. So let's try the epsilon delta definition. So we could say, this is again from Stewart. So if f is defined on a subset D of Rn, then, it doesn't say then the limit as x, this is a vector, goes to another vector A of f of x equals L means that for all epsilon greater than 0, there exists delta greater than 0 such that f of x minus L is less than epsilon whenever x is in the domain of F, and I guess I should call this domain D. Whenever x is in the domain of F and 0 is less than x minus A is less than delta. So you can see that this is definitely a relatively straightforward generalization of what we used to be working with earlier in this class, which was single variable calculus. And now we're having the case that we have functions of many variables, and that if we look at the norm of the difference between my vector x and the vector that I'm bringing it toward in some sense, if I check that the norm of this difference is between 0 and delta, and that then no matter what epsilon I choose, I can always find a delta that makes f of x minus L less than epsilon whenever x is in the domain and 0 is less than the norm of x minus a is less than delta, then I would be able to say that the limit as x goes to a of f of x equals L. And so you can also see that this is the generalization of the statement that's up here, which said essentially no matter how you approach this AB point, which would here would be this vector A, no matter how you approach it, no matter what path you're on, you still have to be able to eventually get the same number for f of xy. And so now let's move into derivatives. So there are more than one way of talking about derivatives when you have multidimensional space. And so one that we often talk about is partial derivatives. And as a reminder, because these are very important in dealing with optimization problems, the partial derivatives, which here we're going to denote as fx, so this is the partial derivative with respect to x. And here's fy of xy, which is the partial derivative with respect to y. So what these are going to be defined as is they have a similar idea to them to the original types of derivatives we were looking at earlier in this class, which were for single variable functions, in that they have a limit. But here it's going to be f of x plus h comma y minus f of x y over h. And you can definitely imagine this extending to many more dimensions. So if you had like x, y, and z, then of course fx of xyz, then you would only again change the x plus h, you wouldn't change the y or the z, etc. So you can imagine this extending to many more dimensions. And the limit as h goes to 0 of f of x, y plus h minus f of x, y over h, and so on and so forth if you have higher dimensions. And so when we say that something is differentiable, it's about whether or not the partial derivatives exist in our continuous. So here, if fx and fy exist near a point AB and are continuous there, then f is differentiable at AB. And so really briefly then, to just state the chain rule when you have multiple dimensions, if people remember when we had the chain rule with a single dimension, we would say, okay, if y is equal to f of x, so this was a scalar x and a scalar valued function f of x, and then we said if x is equal to g of t and f and g are differentiable, then we said that dy over dt is equal to dy over dx, dx over dt. And so this was how we did the chain rule in our past, is that we said, okay, so since f is a function of x, but x is a function of t, that means that y changes as t changes, and the rate of change of y with t is given like this. And so now what we're going to do is we're going to just write out the general version of the chain rule for a multi-dimensional function. So in this case, it would be that we have u is a differentiable function of n variables. So it will be u is a function of x1, x2, x3, dot, 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 xn, however many there are. And remember that we just said what it would mean for this to be differentiable. So it would be differentiable at a point if all of its partial derivatives exist at that point. And so it's going to be differentiable on a domain if all of its derivative exists at every point and are continuous at every point on its domain. So it needs to be a differentiable function, and every xj is a differentiable function also. Of t1, t2, ... tm. Then implicitly, the u is a function of all of these, the t1 to tm. So we could do derivatives of u, partial derivatives of u with respect to each one of these, because u is a function of all of them, so it does have to be a partial derivative. But in addition, it's a function also of the x, so it will be du dx1 over dt1 plus du dx2 over dt1 plus ... plus du over dxn over, oh, sorry, these should all be ti for consistency with that this is an I right here. dti for all I equals 1 to m. And so you can see then that because each x is a function of all of these, we look at the way that the u changes with respect to each x and each x changes with respect to each I. And so there you go for that. And this can be very helpful in some of the things like understanding some of the algorithms for differentiation and things like training for neural networks and stuff like that, where you have to look at the ways that an output of a neural network changes with respect to certain variables that might be functions of other variables and stuff like this. Like if you want to know how your output changes with respect to certain variables that are dependent on others in a neural network, for example. Okay, so now we've talked a little bit about these partial derivatives in x and y, but if we look back at what we are dealing with here, partial derivatives are going to be important in our gradients, but it looks like we don't just have a just like a normal derivative in some of these cases, right? So this one looks like a normal gradient vector, but then we also have all of these ones that are evaluating derivatives at these points x plus tp. And so let's try to understand this concept of looking at cases where you're not just looking at the derivative of something at x, but where you could also add these other points. Now, of course, what this means is it means take the gradients. So it means to do the normal gradient vector and just evaluate it at this point x plus tp. But then there's also something called directional derivatives that help us better understand a concept of directionality, which is sometimes used in describing this concept of this type of t thing. And so we're going to talk now about directional derivatives. So directional derivatives. So this is if you're going to have a rate of change of a function of two or more variables in any direction. And so what do we mean by in a direction? Well, when we do something like fx of x0, y0 is equal to the limit as h goes to 0 of f of x0 plus h, y0 minus f of x0, y0 over h, we could look at this and say, that this is really the rate of change of f in the direction of like 1, 0, essentially. So we're looking at what if we change x0, or what if we don't change y0, but we change x0 by a little bit, so that then effectively we would be moving in this direction and seeing how f is changing. And so you would get something similar for the partial derivative with respect to y. Now we can also though say like, well, what if I don't just want to look at like in the direction 1, 0, I want to look at how something is changing in another direction. And it's easier to see why this would be motivated if we look at a picture and then we think about things we might want to do. So here we have y and we have x and we have z. And so here is like a surface in multiple dimensions. So it happens that if you're still in, if you only have a function of 2 variables, you can still actually draw it well enough to look at it. So this is if we have z is equal to f of x, y. And so here's this surface. And then we could look at this in the following way. So we're going to make an initial point, z0 equals f of x0 and y0. So let's find this initial point. So here's my point, z0. And so it would be defined by this point P in this 3D space at x0, y0, z0. So this is my point that has z0 right there. Now, this point P is on the surface because it is the z value that's equal to its right-hand side, and this right-hand side defines the surface as long as the left-hand side is equal to the right z value. So this point P is on this surface over here. And so let's say that we want to look at a unit vector u equals AB. So this is no longer only along the x-axis or along the y-axis. It now is in a different direction, something like going this way over here. So there is a plane, if we look at this direction. So here's the direction u, let's say. And so we could draw like a plane over here that will cut through the surface. And so if we look at this plane that goes through the surface in the direction of u, then there will be this curve over here, C. We'll call this C. So the curve C is the intersection of the surface with the plane in the direction of u. I guess I should say the vertical plane. And so then we could get a tangent to this curve. And we would say, okay, so let's get the tangent to this curve right here at the point P. So the slope of the tangent to the curve to the curve C at P is the rate of change of z, z in the direction u. And so what that means is that if I was to look in this direction u, I would be able to see how much is this changing. So how much is the z value changing when I move in this direction u at this point P? And so we can start to see then why this might be valuable to us. And that in fact, we would be able to say, okay, well, let me think about this. So say there's another point on my curve here, and this point on my curve is Q. And so Q is some point X, Y, and Z. And then say that I like drop a vertical here. So perpendicular and perpendicular right here. And so let's, these are projected, these are the points P and Q projected onto the XY plane. So let me call this one P prime and let me call this one Q prime. And so in this case, we can see that this line through P prime and Q prime, P prime, Q prime, is parallel to the U vector. And so what this means is that we should be able to write P prime, Q prime is equal to some scalar multiple of U, HU equals HA and HB. And that's for some scalar H. And so therefore I could say, okay, so how much did the Z value change when I was looking at this? So when I go from this point Q to this point P, how much did my Z value change? And so we could say, oh, okay, well, the change of Z with a change in this H, so that would mean like essentially how far down this line I'm going, because you can see that the H here is playing the role of sort of how long is this vector. And so a change in Z with a change in H would equal Z minus Z0 over H, which would be F of X0 plus HA and Y0 plus HB minus F of X0, Y0, and then divide by H. So you can see that this is what we would get if we want to say like, okay, so I make a change in Z with a change in H. And then that would give me that my original point is this X0, Y0. And then as I go from this point P prime to this point Q prime, I go HA units or HB units. And so I add those up and I say, okay, here's the new value of Z. And then I add X0 and HA and Y0 and HB, and that becomes F of that new point is equal to Z. And then F of X0, Y0 is Z0 and divide by H. And then we can say, okay, well, so this means that as I go some distance in that direction along the unit vector, I could say, what is the limit as that length of that vector, or the length of the distance between P prime and Q prime as it goes to 0? So if I take the limit as H goes to 0 here, it gives the rate of change of the Z with respect to distance in the direction of U. And this is called the directional derivative of F in the direction of U. And so this is actually the same as the partial derivative fx or fy, etc. If you are looking at those, but that would be in a very specific direction. So if u is equal to 1, 0, you get the fx. And if u is equal to 0, 1, you will get fy, and so forth and so on. And so it will generalize. And so In this case, we make a few more notes about the directional derivatives. And so let's just finish the definition then. So first, now that we've sort of stated these things and we have some intuition graphically, which of course something like this can hold in more than 2 dimensions, but then it will get much harder to visualize. So here is just what the definition of the directional derivative is then after that. So the directional derivative of f at x0, y0 in the direction of a unit vector u equal ab is sometimes can be noted like this. Du f of x0, y0 equals the limit as h goes to 0 of f of x0 plus ha, comma y0 plus hb minus f of x0, y0 over h, if this limit exists. And so you can, again, imagine extending it to higher dimensions. And so as an important note, here's sort of just a theorem, which can be proven, but it's that if f is a differentiable function of x and y, then f has a directional derivative in the direction of any unit vector u equals ab, and this directional derivative of f of xy is equal to fx of xya plus fy of xyb. And so you could go through and make a proof and involve some stuff about the chain rule and stuff, but there you go. So there are directional derivatives. And so now let's also talk about gradients. So now we're going to learn about gradients. So directional derivatives are important in some of the proofs of some things that come up in the optimality theory, and that also gives you some notion of the idea of thinking about going in directions, so that when you see stuff like this x, the derivative of the partial derivatives of f, and you see that they are, or the gradient of f evaluated at x plus tp, even though the gradient itself is going to include the partial derivative. So that's a form of a directional derivative, but that's not really, I guess, in a special direction of any type. But then if you evaluate it at this point, x plus tp, then you can think of that as evaluating it. You can think about like kind of directionally that the t and the t here, as you change it, is changing this position. So you can sort of think of it as contributing to some notion of like where x is at. And so now I'm going to just remind us of the gradient notation, because that's the stuff that we actually have over there. Even though directional derivatives are important in some other proofs, probably not ones that we're going to write, but at least it gives you a larger picture here. So the gradient vector, which is what we have in the proof. So the gradient vector is very specifically defined as del f equals, and then you would take the derivatives with respect to all of your components, would be like fx, fy, fz, for example, if you're only having the derivatives in 3 directions, but you could imagine it going on and on and on. So So now we're going to cover an important point. So first, I want to note that the directional derivative f(x, y, z) is equal to del f x, y, z dot u. And you might say, oh, how do I know that? Well, the way that I know that is because of this. So what this says is, it says that if you take the gradient vector, you dot it against the unit vector that you're going in the direction of, that you are going to get a the directional derivative in the direction of whatever you dot it with. Okay, so now we're on to something. So we are able to see here that right here we have some different gradient vector dotted with another vector. And so we can have some hint that, like, okay, there's probably something that is important to the idea of directional derivatives, because it seems like this is sort of a form that is reminiscent of that. So let's talk then about the idea of maximizing the directional derivative. So in this case, here is the question that we can ask. So we want to say f is a function of more than one variable. So f has many possible directional derivatives. At a given point, because I could look at the derivative of f among in many possible directions. And so even if you look back here, you could imagine, okay, well, I could have rotated this u vector, I mean, in any direction here in the xy plane, and I would be getting different directional derivatives. And so same idea here. And so then you could say, okay, so in which direction does f change the fastest and what's the maximum rate of change? And so in this case, we can say that the answer is del f of x is the maximum value of the directional derivative. So the maximum value of any directional derivative we can have is this, and this u right now, though, is undefined. So I didn't say yet which direction that is, but then we can say, okay, well, it is for the u in the same direction as the gradient del f of x. I'd say, what? Where's that from? How do you know that? Well, it's that if you have this duf is equal to del f dot u, which could also be written as del f transpose u, equals. And so this, just by the definition of dot products, is del f norm u norm cosine theta, which, because u is a unit vector here, this is equal to del f cosine theta, because the norm of the unit vector is going to be 1. And we can say that, okay, so theta here is the angle between del F and the unit vector. And this is going to be the largest for theta equals 0, meaning that del F and U are parallel or in the same direction. And so then the one other thing I want to do is the review from calculus before we go back to our optimization stuff is to say, okay, let's look at a tangent plane to a level surface. So we're going to have S is a surface where f of x, y, and z is equal to k. So we would say this is a level surface of a function f of 3 variables, meaning that it is the set of all of the x and y and z points that cause f of x, y, z equal to k. And so P of x0, y0, z0 is on S, and C is a curve on the surface. That passes through P. So because C is a curve, the things that we started with at the beginning with the vector functions is going to hold. So we can define this curve as x of t, y of t, z of t here, if we're looking at this function of 3 variables. So here's the description of C as a curve. And say that this r of t0 is equal to p, because that would equal x0, y0, and z0. Let's say that that's how that works. So then, because C is on S, then it has to be true that any x of t, y of t, z of t on C also satisfies the equation that all points on S must satisfy. Which would mean that f of x of t, y of t, z of t would have to equal k. That's the equation up here that all the points on S have to satisfy. So then we can use our chain rule over here and say like, okay, well, if the x, y, and z are differentiable functions of t, then this f is also differentiable. So I'm going to say that, okay, so the derivative of f with respect to x, dx over dt, so I'm differentiating f with respect to t, plus df over dy, dt, plus df dz, dt. So this is some type of implicit differentiation of my left-hand side, and I'm going to say that it's equal to 0 because that would be the derivative of the right-hand side with respect to t. And so at this point, we know this much, and we can say, okay, so this is true, but then also I could rewrite this as the following. I could say, okay, well, let me write this as the dot product of two different vectors, one of them being the gradient, which here would be fx, fy, and fz. And this is going to be this part, fx, fy, and fz. And then I'm also going to say, oh, look, this other part, these parts, these are all the derivatives of the components of R. So like we said earlier, when you have a vector function, the derivative of the vector function is the derivatives of its components. This would say R prime of t is equal to x prime of t, y prime of t, and z prime of t. And so what this would mean is that then I can rewrite this expression as del f dot R prime of t equals 0. So then we have to think about, what does this say? So let's go back to our time t0 and our point t0. So what this would mean is that at t is equal to t0, then R of t0 is equal to x0, y0, z0. So that's what we said earlier when we said this point. And then we also have that del f of x0, y0, and z0 dot R prime of t0 is equal to 0 because this relationship holds for every one of the t's, including t0. And so what this says is that the gradient vector at P, and then this tangent vector to the curve C on S that passes through P, when you dot these two, they equal 0. So this means that they must be, these are perpendicular. And so what this would mean is, like, if we go back and we have our surface over here, x, y, z, here's the big surface, and here's some curve that passes through the point P and lies on the surface. And then we can get the tangent vector here. So this is going to be R prime of t0. And then here we have this perpendicular vector, and this is del f of x0, y0, z0. And so those are the main things. So let's just go back and say, okay, what was this lecture just about? Well, what this was about is the following. That we started off by saying, okay, I'm looking at optimization, and I can tell that there's some things I'm going to have to remember. So just from looking at this, I can tell that I'm going to have to remember the difference between a function mapping from R to Rn versus Rn to R. I'm going to have to remember what it means for functions of multiple variables to be continuously differentiable. I'm going to have to be able to then look and say, okay, what is the gradient? What does that mean to evaluate it at a point, which here would be the point x plus tp? How is evaluating gradients at points distinct from directional derivatives? How is it related? And then things like that. And then so we went through all these things and we talked about, okay, vector valued functions or vector functions, when you map from R to Rn instead of Rn to R, our objective functions are going to map from Rn to R. We did some of the things talking about what curves were, which turned out to be important at the end of the lecture, what different definitions of continuity and differentiability were. We talked about what it means to have limits and epsilon delta limits. And then we talked then about what it would mean to have a partial derivative and for a function of many variables to be differentiable, which would mean that its partial derivatives have to exist and be continuous at the points where the function is differentiable. We briefly reviewed our chain rule for functions of many variables. And then we got to the conversation about what is a directional derivative, which turns out to have usage in some of the things that we'll be discussing in the next lectures for optimization. And so we said that this is related to a rate of change of a function of multiple variables in a specific direction. And we drew this plot to sort of show what that would mean, how you would look maybe at the values of this function of two variables, but you would not just look at them, you would not just be looking at, okay, what if I only make changes in the x direction or the y direction? You could look in various directions and see what the changes are in the value of the function as you make a change in the distance that you look in that direction. And so then we said that the relationship of that with the gradient vectors, and that we would be able to write our gradient like this, and then our directional derivative as the gradient dotted with the unit vector in the direction that we are trying to look at our directional derivative. Then we talked about this concept of maximizing directional derivatives, where we said that if f is a function of more than one variable, so f has many directional derivatives at a given point, then which is the direction which is going to cause f to change the fastest and have the greatest rate of change. And we were able to say that the direction which f changes fastest is going to be the direction of the gradient, and that in that direction, the maximum rate of change is going to be the norm of the gradient. And then we also talked a little bit about tangent planes to level surfaces. And in particular, what we came up with is that the gradient vector at a point P on a surface is going to be perpendicular to the tangent line through a curve lying on C that passes through that point. And then, through a curve lying on the surface S that passes through the point P. And so now if we look back really quickly one last time at what we had at the beginning, we can see that we have this notion of x plus tp. This means just evaluating the function f at the vector x plus the vector p. So this so far has nothing to do with directional derivatives. This is just evaluation of f. Similar for this is evaluation of the gradient at x plus tp. But we can start thinking from what we've been discussing. We can say like, oh, if this was in like a multi-dimensional space, I can see how the t is in some sense related to like the way that I'm changing x, and that if I consider my p, that that I could say like, okay, like the x, if that is a certain vector, and then if I'm sort of changing this t, that will take me different fractions of p away from x. And so you could say like, even though here, this is asking for the derivative of f, or all the partial derivatives of f evaluated at x plus tp, that's what this means. But from the discussion that we've had, we can think about kind of what that would look like spatially to see x plus tp. We can see that there is some sense in which there's a gradient transpose a vector p. And so we can say like, oh, that's interesting, because here was another case down here at the bottom where I saw a gradient transpose another vector, in this case, a unit vector u. And so this sets us up with some helpful background on calculus to then be able to go back to our optimization fundamentals and start to try to piece together all of these things we just covered to try to derive some of the important things in the fundamentals of unconstrained optimization followed by constrained. All right, so with that, I'm going to stop this recording and we'll make another.